Pessoal, bem-vindos aqui ao colóquio do Instituto de Física. E eu vou direto ao ponto, então vou convidar o professor Raul para fazer a introdução do nosso convidado hoje.
Obrigado. Para quem não conhece a área, hoje é um grande prazer ter o Romeu Davé aqui. O Romeu é atualmente Chair de Física da Universidade de Edimburgo, na Escócia. Ele fez a graduação em Berkeley, o mestrado em Caltech e o doutorado em Santa Cruz, onde ele começou a trabalhar com simulações cosmológicas. Depois ele foi fazer pós-docs por aí, em Princeton, e foi Hubble Fellow também. E desde... since when are you in Edinburgh? 2017. Desde 2017, ele está em Edimburgo. Edinburgh. Aprendi pelo menos a pronúncia. A área de pesquisa do Romeu é principalmente simulações cosmológicas. Ele foi uma das primeiras pessoas que incluiu não só matéria escura, mas bárions, ou seja, átomos e radiação, e fazendo, portanto, essas simulações se tornarem muito mais realísticas. Inclusive, você pode enxergar e colocar a formação de galáxias nas simulações, e elas são super úteis em várias áreas de cosmologia, em particular nesses levantamentos astrofísicos que combinam muitos dados de muitos lugares diferentes. Ele também escreveu um livro de divulgação, que em 2023, que eu acabei de pedir para a nossa biblioteca comprar. Eu ainda não tive tempo, I haven't had time to read your book yet, but parece muito bem recomendado. Simulating the Cosmos, enfim. Então é isso, é um grande prazer ter o Romeu, and that's it. Thank you, Romeu.
Okay, great. All right, so yeah, thanks very much, Raul, for inviting me to give this colloquium. Let me share my screen, I think. Okay, great. Yeah. So, as Raul probably told you, not entirely sure, I do simulations of galaxy formation. So in this lecture, essentially what I try to do is introduce you to, what these sorts of simulations are, how we do them, why we do them, and also tell you a little bit about our group's particular simulations and some of the more interesting results that we have gotten in this game. We're certainly not the only group doing these types of simulations, but I think, hopefully you'll get a flavor for what is some of the questions that we're trying to ask and learn using these simulations. Okay, so what is the basic problem here? Okay, so this that you're seeing on the screen, maybe some of you have seen this before, but this is an actual picture of our baby universe, okay? It's taken with a telescope, in fact, 3 different telescopes at different years, and you see how things have improved in terms of the resolution that we can get. Okay. Why is that not working now? I'm not sure. Okay. It was working a minute ago, wasn't it? Yeah. Okay.
Turn it off. So, on-off button here. No.
All right. Well.
Stop working.
Okay. In any case. Okay. Anyway. So yeah, so this is basically an actual map, and what you're seeing here is temperature fluctuations in the cosmic microwave background. So people have called this the echo of the Big Bang. Effectively, it's a space-filling sea of photons that today has cooled down sufficiently to be at a typical black body temperature of 2.73 Kelvin, right? Now, what you're seeing here is effectively gravitational redshifting. So there's small matter fluctuations at this time, and very, very small fluctuations. So we're talking about few parts in 10 to the 6 in fluctuation. So extremely, stiller than any pond you've ever seen in your life. And then these fluctuations, nonetheless, are, when the photons escape to us and travel freely since the time of recombination, when the universe became transparent, then effectively, there are these small fluctuations in the temperature that we get in the photons in our telescopes. And that tells you about the spectrum of perturbations here. So that's very nice. So we can actually take images of this, of our baby universe, you know, very cute. So then we go out and take a picture of the universe today, and it looks very different, right? It looks much more like this, okay? So this is an image from the James Webb Space Telescope of the particular patch of sky that's probably, it's about as big as your thumbnail held at arm's length, okay, on the sky. So that's a typical size of this image. And you're seeing thousands upon thousands of objects, and that's just what you can see with your naked eye. The computer can pick out much more. The point is, each of these objects is highly nonlinear object, right? Pretty much anything that you see in here that's shining, with the exception of a few of these spiky things, are galaxies. Okay, so there's collections of you know, millions, billions, trillions of stars very far beyond our own Milky Way. So that's great. So this is effectively the problem that we're trying to solve, right? How did we have the initial conditions, great, right? So the question is, how do we get this 14 billion years later? So that's the problem of galaxy formation, and the thing about it is it's a very big field, primarily because it's a field that is at the center of so many different subfields of astrophysics, right? It's probably the largest subfield in astrophysics today. So, you know, you have to start with cosmology, you have to start with the origin of the universe and the Big Bang, you know, to understand where everything came from, including galaxies. But galaxies are made up of stars, so that means that we have to understand how stars form and how stars evolve. They don't just sit there and do nothing. They do all kinds of things like explode. When they explode, in supernovae, they can create heavy elements. At the time of the Big Bang, the only elements were hydrogen and helium, pretty much. And everything else that we get today that is heavier in the periodic table was all synthesized within this process of some sort of stellar process, right? So we have to understand that. The universe is filled with dark matter, as many of you probably have heard of. So dark matter makes up about something like 25% of the total mass energy budget of the universe. The stuff in the periodic table only makes up about 5%, okay? And the rest being this mystical dark energy, which is a very interesting problem, but I won't be talking much about it today. We've learned for the last 20, 25 years that just about every sizable galaxy has a supermassive black hole in it. So what's that doing there? Where did that come from? And not only that, worse, you know, even, is that these black holes seem to have a big impact on their galaxies. And so why? How? How does that work? Okay, and that's one of the key questions today, and something that I'll talk a lot about later. In general, galaxies have a lot of processes that release energy as they form. Okay, so you know, you might think that galaxies formation kind of a one-way process where gravity just brings things together and collects matter into a spot, and suddenly you have a galaxy. Great. Okay, you know. That scenario really doesn't work very well. It doesn't produce galaxies like we see. Galaxies instead seem to be highly self-regulating systems, and we'll talk about why. And this category of processes called feedback represents all the various ways in which galaxy, during their formation, can release energy in order to retard its own growth. And that could include supernovae energy, could include black hole energy, lots of other things. Right? Okay, so this is the problem we're trying to understand. But let's get a little bit more into galaxies to figure out, you know, exactly what the bar is for understanding stuff here. So we now have huge surveys of all these galaxy populations, not only today, but going all the way back in time. You know, now I think currently the highest redshift galaxy, or the farthest galaxy, is something like, you know, 400,000 years after the Big Bang, something like this. Maybe even less now. But generally, at least today in the nearby universe, galaxies come in two types. Okay. In point of fact, it's slightly more. There's a whole classification scheme that Edwin Hubble came up with. But you know, for the most part, these two types are these elliptical type galaxies and these spiral galaxies. This is one of the closest analogs to the Milky Way that we can find in the local universe, M101. Okay, so you know, Hubble noticed this in the 1920s, okay, Remarkably, it's still not entirely solved why this happens, okay? There are not a whole lot of things in between, it turns out. But it's even more interesting than that it's not just the shape of the galaxy that divides into the two classes, but there's a huge number of properties associated with each of those shapes, okay? And so with elliptical galaxies, at least the biggest ones in the universe, the biggest galaxies in the universe all tend to be ellipticals, okay? Why is that? These ellipticals seem to have no current new stars being formed, or very few. That's weird, because they have a lot of stars, right, if they're the biggest things. So yet they're not forming anything right now, right? Which means most of their stars are old, right? They have to be if they haven't formed anything new recently. Which also means that they're red, okay? So stars evolve from sort of being blue and bright to being old and red. The blue bright ones all explode and go away, leaving the only, it's like Hollywood. All the stars blow themselves up at an early age and disappear, and then all that's left is the normal plebeian folks, right? Which are the red stars, right? They have a lot of hot gas, and they tend to live in dense environments. They tend to have no dust, and they tend to have a very large black hole compared to the spiral galaxies. And by large, I mean something like 1 over 200 or 1 over 400 times the mass of the total galaxy, right? So not hugely important dynamically, but as we'll see, it's very important for other things. The spiral galaxies, again, not only a different shape, but kind of have the opposite set of properties, all right? So again, what sets all this? Why do the galaxies come in these sort of two flavors in general? There's many exceptions to this rule if you look around, but generally speaking, this is true. So that's another thing we have to explain if we want to understand galaxy formation. Okay, so obviously this process is highly nonlinear, right? You can see galaxies today are extremely nonlinear objects, and there's lots of different physics going on, right? So this is why we sort of go towards simulations, to try to understand it in a very dynamical context within a full sort of cosmological setting. And so what would we like to do? Here, what if we can just magically, flip the switch and say, let me just have everything I want. So what I would want is to simulate a representative cosmic volume. So that means a large enough volume that I can sort of statistically, have all the galaxy populations represented from the Big Bang until today, including all the relevant physics that's required to form galaxies, whatever that is, and end up with a realistic-looking galaxy population. So that would be great. So why would that be great? What could you do if you did that? Well, one of the more important things is that we as astronomers have a big problem compared to a lot of other sciences, that we don't have a lot of control over our experiment, right? It's out there, we're here. So if we want to run experiments, how do we do it? Because experiments are kind of fundamental to the whole idea of science, right? So one of the ways to do it is to create this platform, right, where we do have control. And we can turn off individual pieces of it and say, well, what would that look like in the real universe? So that's a way to try to understand what set of physics is required to form galaxies. Right? If you turn off one piece of physics and it does nothing, you think, it's not that important. If you turn off a piece of physics and suddenly everything changes, you think, oh, okay, right. So this is one of the key ways in which we try to learn about the physics of galaxy formation. We'll talk about some examples of that. But also, right, one of the nice things about simulations is that, in principle, they contain everything, right? We're modeling the whole universe. So, okay, down to some scale, and we have limitations of computation and so on and so forth. But, in the range of applicability, we should be able to model everything, right? So that means, we can look at, with all these incredible new telescope facilities where, each of these basically is at least $1 billion, right? This one's more like 10, right? So we're spending a huge amount of money on all these telescopes. And as great as they are, let's face it, JWST, it's a fantastic telescope, but it only sees in the infrared, right? It doesn't see in the millimeter, doesn't see in the radio, This is an optical telescope built down in Chile, over in Chile, right? Or X-ray, right? Okay, So we have all this differing data, but how do we connect them, right? How do we know, that what we're seeing in each case and what it's telling us? Well, simulations give us a chance to do that if we can turn our simulations into observations somehow. That's a whole industry in of itself, but if we can do that, right, then we can interpret observations, say, hey, that same galaxy you're seeing with JWST, this is what it should look like in the radio, or this is what it should look like in the X-ray, allows more testing in the model, and allows us to sort of connect across these multi-wavelength surveys. So that's why we're trying to do it. Why is it hard? So it's hard for two main reasons. One, we don't know the physics, and two, we don't have big enough computers, right? So there are many, many physical processes. I showed you that big, circle of death of all the various processes that go into galaxies. Some of them you can sort of try to model. You think, okay, I can write down equations for things like gravity. Okay, I know Poisson's equation. I can figure out how to solve it on a computer. I know hydrodynamics, shock heating, et cetera. Radiative cooling and heating, okay, those are quantum processes, with electrons switching atomic levels or whatever, or getting ionized. I know how to do that as well. But then there's a lot of stuff we don't know, right? In particular, we don't really know how star formation occurs, right? That's a whole separate field in astronomy, is people trying to figure out how stars form. Similarly, black holes. We don't really understand that terribly well. Even chemical enrichment. Okay, so people know that these elements are created in supernovae or in stellar compact object mergers or whatever, but exactly how much, why, when, still. And certainly all these sort of energetic release processes and how that self-regulates galaxies is very poorly understood. So all of this is what we term subgrid physics. Grid, not necessarily that we use grids in our simulations, but we call it that anyway, right? So these subgrid physics, this is where all the action is in some sense. I mean, you can make some different choices here for how to solve things on a computer, but ultimately, the big uncertainties are down here, right? So that's one thing, is we don't actually understand the physics yet, okay? And then the second part is that the dynamic range that we want is enormous. So roughly, right, the universe is, again, very order of magnitude, about 1 billion, about 10 billion light years across, really. And, the stars' typical stellar distances are sort of like, a light year, to its nearest star for us is 4 light years, right? So that's a dynamic range of 10 to the 10. That's one spatial dimension. You do 3 dimensions, that's 10 to the 30. So if you wanted to populate your computer, you would need, 10 to the 30 of memory at least. Well, of course, that's just for one quantity, however many quantities you have. And then of course you would have to figure out, how many cycles it takes to evolve that. It's a lot, right? It's completely unfeasible. Just to give you an idea, right now people are pushing the limit of about 1 trillion particles. So that's 10 to the 12. Okay. So you have to make choices. You have to say, okay, we're not going to do the whole problem at once, but maybe we can break this up into chunks, study them, and then try to piece things together, right? And that's what we do as simulators. You can try to model the whole Hubble volume, to a gigaparsec size volume, so whatever, billions of light years. But of course, that means your resolution is very, very coarse. You're probably not going to really see individual galaxies all that well. You can sort of do cosmological simulations, which are kind of like, up order, 100 megaparsecs, which is, a few hundred billion light years. Then, you have representative volumes, but you're not getting the internal structure. You form galaxies, but not getting maybe the internal structure super well, or detailed processes not well. And then people have started to do these zoom simulations. I'll give you an example right here. This is a zoom simulation of a single galaxy cluster. And then you can sort of take out pieces of that and re-simulate just that little piece with much higher resolution. So you only get one object or one small set of objects, so you don't get the statistics that you do in the cosmological case, but you can study the process in much more detail, right? And then by piecing all these together, we hope to sort of, get a more complete picture of what's going on. Okay, so yeah, so basically this is highly nonlinear. It's chaotic, right? It's formally complex because it's self-regulating. So it's not amenable to analytics. And the idea of it is very simple. Of course, it sounds so simple. You wonder what all the fuss is, right? You just have a bunch of particles in a box, and each particle represents some piece of mass, and that particle could also have a type. So it can be either a dark matter particle, and you think, okay, dark matter, at least on large scales, only interacts with gravity, so we only have to worry about gravity as a force there. But for other particles, which are gas particles, right, there we have to worry about Euler equations and all these sorts of things, right? So then we have to solve an additional set of equations for those. So then, and then of course you need thermodynamics for those, so on and so forth, and then all the subgrid models, right? So that's great, but the idea otherwise is fairly simple. You take a given particle, so this is a 6-body simulation here, right, that I've just drawn very, very, very crudely. You compute the forces, you choose some time step delta t, give you an idea, a typical cosmological simulation has a delta t of about 1 million years, okay, roughly, give or take, probably a little less actually. So then, just using very simple things, you can advance the velocity of the particle, so you increment the velocity in some direction, and that allows you to increment the position in some direction, and then you have a new set of positions for your particles where you can repeat again. So, and you just do that for 13 billion years. And so this is the kind of thing it looks like. This is a simulation was showing the stellar star component, so we've had some criteria for turning gas into stars when it becomes very dense. This is the gas density, this is the gas temperature, and then these are the heavy elements, that are everything heavier than helium, right? And what you'll see is you form this sort of network of filamentary structures. Okay, this is just a natural outcome of gravitational instability. You don't have to do anything fancy for that. And these, as time goes on, of course, these denser regions are attracting more and more material. And they're the sites where you get all the star formation, of course, is these very dense regions where you can collect a whole bunch of matter, which also then releases some energy, because in this model we have some supernovae going off, right? So you have some supernovae going off that causes some increase in the temperature, which you can see here, and at the same time also distributes these heavy elements. We also have, well, this is not my simulation, this is illustrious TNG, but we have sort of galactic winds coming out of the galaxies which distribute these heavy elements further. Now we're going to start to see some black holes coming in. Look at these, right? This is just, again, we have no idea how this works. This is one choice that they made, that the black holes are going to do this. They're going to set off little bombs in the galaxy whenever they accrete a bunch of material. Okay, so it's just it's one model for how to do it, right? And you can see that over time, you start to really change the character of the universe, right? You start to form these very large structures, start to heat the gas. These heavy elements are ending up everywhere, all over the universe. This is a big region of space. This is about, I think this box, if I remember, is something like 50 megaparsecs, something like that, right? So it's pretty large, but you can see that it's kind of amazing. Like when you take a picture with JWST or something, you'll see this panel, right? You'll see the stars. You won't see any of that, right? But all of this is going on in the background, right? And there are ways to see it with other telescopes and facilities, but it is much more difficult, right? The stars are the most obvious thing. So, so that's just an example of how, what you get out of these simulations. So what kind of physics does go into these things, right? So there's, obviously gravity, which is not even listed here, but you also have gas cooling. That's, again, well understood. Interstellar medium, not super well understood, but there's ways to model it that it's not so sensitive to your lack of understanding. Star formation. The one nice thing about star formation, and this illustrates how we go about constructing these simulations, is that there is an empirical relation in the real universe that we can measure. And that is that if you know the gas surface density within a sort of a 1 kiloparsec region of space, it correlates very, very well with the amount of star formation surface density. Again, it's a whole separate field to figure out why that happens. On the other hand, if we only care about things on scales larger than a kiloparsec, we don't have to worry. We just implement that and we say, okay, the universe does it, we'll just do it, and we'll form stars in our simulation. Okay? So that's what many of these models do. And so it's reasonably well constrained, even if it's not all that well understood. Then we have all these sort of stellar feedback processes, supernovae, et cetera, so stellar winds, massive black holes, AGN. People are starting to do things like magnetic fields, radiation fields, radiative transfer, cosmic rays, but usually only in specialized circumstances, right? Not generally. Of course, all these models, particularly these, have a lot of free parameters. So you then have to decide how are you going to constrain those parameters, and typically the way that's done is you try to match some set of observations, right? And so generally matching stellar properties that are observed and the black hole mass properties. So again, you have to fiddle with these things. Each one has to do that themselves. So the tip, again, as I said, you have about a kiloparsec resolution in these cosmological simulations. And this just gives you a little flavor for all the various ones that are around these days. Another thing that's important is like each gas particle, or each particle, represents about 1 million times the mass of the sun, right? So we're not doing anything like forming individual stars or anything like this. This is very coarse compared to that. So that just gives you a flavor for what goes into this thing. Let's, just to give you an example, I'll talk about my simulations. Essentially, we're picking one particular hydrodynamics method, which is a meshless, effectively a mesh, what's called a meshless finite mass. So it's a moving mesh code, you can think about it, with sort of fluid boundaries. So that's very nice because it marries some of the benefits of the adaptivity of being having a moving mesh, but also the mesh allows you to do things like resolve shocks better than if you use some sort of smoothing code. Then we try to include star formation. We know that star formation forms out of molecular gas, so we have a way to form molecular gas, create the stars. That requires cooling the gas down, right? And so we implement all this package called Grackle that follows all the radiative cooling processes and heating processes. And then, we have things like on-the-fly self-shielding for various, against a metagalactic ionizing background. In this version, we're tracking 9 elements, plus hydrogen and helium, so sorry, I guess that's 11. And then including cooling from those species as well, which turns out to be quite important, right? So these are all the things you have to basically take your basic code and start building on them, right? Various packages. Then we start to include all these sort of less certain processes, like star formation feedback. Now, the way we've done it, right, which I think is starting to catch on now more and more, is to say, okay, we don't know how this works, but we have these Zoom friends over here running these much higher resolution simulations. Maybe they can tell us how it works, right? And in fact, they can. So I partnered with another group, which was the fire simulations, which are quite a famous group of people who do these very, very high resolution Zoom simulations, where you try to model things much more from first principles, but again, only on a galaxy by galaxy basis. But that's okay. Turns out they come up with some scaling relations based on things that we can then implement into our larger model, right? So that's kind of the idea of how that's done. We'll talk more about the black hole stuff because I think that's one of the most interesting aspects of SIMBA. And then the black hole feedback. We also produce dust and on the fly. So the things listed in, actually I should put that in purple too. Things listed in purple are basically things that SIMBA has that no one else has, right? That other people have things that they have that SIMBA doesn't have. So everybody has their own decisions to make as to how to do these things, right? Okay, so what makes SIMBA unique? Some of the basic things, right? I've kind of mentioned this already. The Gizmo meshless finite mass method is quite nice in the sense that one of the things it does, for instance, is if you have a disk of gas in equilibrium and it's a rotating disk, you would like it to stay there, right? If it's in equilibrium, shouldn't do anything. Well, most of the codes these days that are used in a lot of galaxy formation simulations do this. Not so good. Okay. That's because essentially this technique that's commonly used for smooth particle hydrodynamics tends to have a lot of shear viscosity, right? And it tends to then lose energy and create these clumpy structures that shouldn't exist, right? You can try a grid code, but grid codes are also problematic because they kind of impose a Cartesian grid. And when you try to advect material at angles to the Cartesian grid, okay, it ends up being tricky. So this is what Gizmo does after 100 rotations. So that's the kind of thing that's the way we try to look to improve how hydrodynamics works, right? The star formation, as I mentioned, was parameterized using the fire zoom simulations. Actually, there's not a lot new here. I just wanted to show you some pretty pictures here. This is the fire simulation, so this is very high resolution simulation of an individual galaxy. And this ends up being the scaling relation for the amount of mass ejected due to supernovae from a galaxy versus the stellar mass. And these data points are all from fire, and you see they lie along a beautiful relation. Not entirely clear why that happens, but that's what comes out of the fire simulation. We can measure in our large-scale simulation, we can measure the stellar mass. We can't predict this, but we can just look it up, right? And that's the kind of thing we can do, right? Black holes is sort of torque-limited accretion is nice. We include black hole feedback in a very bipolar way, which is also fairly unique. And we have a lot of dust, which turns out to be pretty interesting for dusty galaxies, which I won't talk about too much today. Okay, so let's talk about this black hole growth. So black holes, I would say, are sort of one of the main frontiers, one of the 2 or 3 big frontiers in understanding galaxy formation. How do the black holes impact the galaxies? Et cetera, et cetera. To put black holes into simulations and put their effects into simulations, you have to start by forming a black hole and then growing it, right? Okay, so how do we do that? There are kind of 2 scenarios you can envision, right? One is a black hole is sitting in a cloud of dispersion-supported gas, right? Or not even sitting, but can be moving with respect to it. And if you remember your, so maybe some dynamics class or something from a while ago, Bondi, Hoyle, and Littleton in the 1950s worked out how much accretion would happen just due to gravity, in a hot medium, right? And they come up with this formula. So this is, for instance, the sound speed of the medium. This is the velocity of the black hole as it moves through. This is the density of the medium. That's the black hole mass. And of course, the rest are constants. So, so that's very good. And it's appropriate when accreting from a static hot medium. But one of the things that people have sort of realized is that galaxies form into disks, right? And stars form in the galactic disks. And probably the black holes are growing while we have galactic disks. Okay, so what's different about that situation? Well, the big difference is that you don't have a pressure-supported medium. You have a rotationally supported medium, which means that if you want to get the material from the large scale of galaxies down to the tiny black hole, remember black holes are tiny, right, spatially, very big in mass, that means you have to lose a huge amount of angular momentum to allow it to get down there, right? And so this is basically a sort of a separate consideration. And so there was some work done, kind of analytic combined with numerical to figure out how that might work, right? And they had a subgrid model for that, which again uses quantities you can compute on fairly large scales. So things like the disk mass and so on and so forth, the gas fraction, et cetera. So basically every other simulation model uses this one alone, okay? We went and said, well, okay, this is really only appropriate if you have a pressure-supported medium, right? And that should occur when you have hot gas. And when you have cold gas, it should settle into a disk, and you should be in this direction. So that's what we do, basically. We kind of say, okay, for a given gas element, gas particle, if we want to accrete it onto the black hole, depending on how hot it is, we will either use this formula or this formula, right? And that's how we do it. And it turns out that, as perhaps shouldn't be terribly surprising, but seems to be surprising to a lot of the astronomers who work on this, this mode by far dominates the black hole growth, right? Disks are where stars form, disks are where galaxies grow, disks are also where black holes grow. Duh, okay. But nonetheless, the both models it's possible to produce realistic black holes in both models. Okay, so then you have the accretion rate, and you have some m dot c squared that is a potential power that you could get out of that black hole. Then how much actually comes out? Well, again, we don't, there's a whole separate field to figure that out, and I would say that they're all over the map in terms of what kind of predictions they make. So instead, we again appeal to observations, right? The same way we did with this star formation, right? So we know that when you have high Eddington ratios, and so by Eddington ratio I mean the accretion rate relative to the Eddington rate being the rate at which balances accretion versus pressure, from the radiation released by the black hole, right? So you have to assume something about how radiatively efficient the black hole is, et cetera, et cetera. But essentially, at Eddington ratios above about 1%, you're in this kind of mode where your accretion disk onto the black hole is so dense that it can basically feed the black hole directly, right? And it's a very efficient mechanism for accreting onto black holes. And it turns out that in this mode, you tend to produce, this is observed, you tend to produce outflows that are coming from radiation pressure kind of blowing stuff off the edges of these accretion disks and the dusty torus, right? So essentially it's the radiation pressure is kind of like skimming off this stuff. And it turns out that the velocities of that are around, 1,000 kilometers per second, give or take, right? Factors of a couple. But something weird happens when you go to low Eddington ratios. You get a very different character for this accretion. And what happens is that instead of allowing the accretion disk to reach all the way to the black hole, you form this what's called a advection-dominated region, right? So instead of, and in fact, this is a little bit hotter, right? And so this is known as hot mode accretion is another way. But the interesting thing that happens is that because it's advection-dominated, as the gas advects inward towards the black hole, it can carry its own magnetic field, right? When it goes through this, it's just kind of going too fast to do that, right? And it can't really form a compact magnetic field. So you squeeze the magnetic field down, you get extremely high magnetic fields. Well, you may have heard of the Blandford-Znaiec process that basically takes a very collimated, extremely concentrated magnetic field. You throw a bunch of hot electrons into it, it's going to be accelerated upwards, okay? It's just, you can use your, V cross B kind of thing, and it's just going to be shot outwards. And it gets shot out at these relativistic speeds. And you see this in the real universe. So here's an example of a galaxy, and here's these relativistic jets coming out that are seen in radiosynchrotron emission. And these are extending out to, 100 kiloparsecs, way beyond the edge of the galaxy. These are huge things before they're kind of run into stuff and eventually stop. So there's a huge amount of energy that's coming in from this mode. So one of the key things that ends up being very important is that when the black hole is accreting at a low rate, it's putting out more energy than when a black hole is accreting at a high rate, which is kind of opposite what you might think. But it turns out to be very key for explaining a lot of stuff. We also actually account for the photon pressure feedback as well. So again, this is sort of a model that we designed based on thinking about observations. Again, that's how we work, right? We look at observations, we talk to people, and we go, what's the best way we can represent the physics that we think might be going on in the real universe at scales of a kiloparsec or so, right? And we do our best, right? So these sort of things makes SIMBA fairly unique. I think among a lot of models, it's been very popular. It started off when I was in Cape Town. Everybody was naming their simulations back then. I had to name something, and obviously I was in Africa, so it was the Mufasa simulations, right? And then the next one had to be Simba, of course, Mufasa's son. But then it's now been done. There's been a large number of little spin-offs that we've had, Zoom simulations of clusters. It's been camels. I think Raoul sort of works with camel stuff. So it's one of the inaugural codes for this machine learning suite. Cosmic Sands, really interesting suite of looking at very high redshift galaxies, particularly nowadays with JWST. SIMBA C is one where we updated chemistry to now follow 34 elements. So we can do yttrium to whatever the heck ratios, which people measure. It's crazy. And they learn stuff from it. Who knows? We have an improved ISM subgrid model that tracks the H2 and the dust much better. So we just put that model out. And then at the end, I'll show you some results from the Hyenas group zoom simulations. So these are a little bit larger, smaller scale than these big cluster zooms, sort of group scale zooms. But this is particularly interesting for studying this black hole feedback. Okay, so we put all this stuff in there. What do we get out? Okay, so the first thing you can say what we get out is something like, what is the history of stellar mass growth, right? And that's shown here. These are the green lines are SIMBA predictions, and the black points are the observations. And these are range from things, today, basically, all the way back to very early universe. And you see SIMBA does quite a pretty good job, right? Not perfect, but pretty good job, right? Also good overall rate of cosmic star formation. So the star formation rate density is another thing you can go out and measure, right? And so those are the black points there. SIMBA is the green curve. Generally gets the right answer, right? So that all looks very nice, right? But it's not just the stars. We can look at a lot of other stuff, right? For instance, this is the stars I showed you, but this is neutral hydrogen, right? So this is where we start to get the multi-wavelength fun, right? So for instance, different bands probe different aspects of the galaxy. That's why we want all this, right? This multi-wavelength data. For instance, in the radio, you can probe neutral hydrogen, turns out, atomic hydrogen very well, okay? So this is our nearby galaxy Andromeda. In the radio, the infrared, the visible, the ultraviolet, and the X-ray, and it's basically tracing, the infrared tends to trace dust, visible, obviously the stars, it's the most obvious thing, like our sun. The ultraviolet traces very young, massive stars, and then the X-rays is good for black holes, right? So you can compare all of these things. Again, SIMBA does quite well at matching all that. That's actually not a trivial thing, right? Okay, so that's all very good. What about other simulations, right? Is SIMBA somehow unique? No, not really. We all kind of get it right. Okay, so these are two other simulations, EAGLE and TNG, illustrious TNG. And you see again at redshift 0 stellar mass function, we get pretty well. If we measure the star formation rate versus the stellar mass, again, the black points are the observations, roughly good, right? Why is it so good? Well, for the most part, most of us have calibrated to this thing. That's why it's so good. Okay, so it's not really a prediction. It's just a calibration. It's not a trivial result. Like 10, 12 years ago, we couldn't figure out how to calibrate anything to get it to work. It was really hard, right? So it's not trivial. Nonetheless, it's possible. But of course, there's huge differences in these models, and particularly if you start to look at some other things, quantities, besides just the stars that we've calibrated to, suddenly things look a lot different. So for instance, here's that atomic hydrogen I was talking about. So what this is an atomic hydrogen mass function. So you look at all the galaxies, you go out and measure their atomic hydrogen, looking in radio, remember, that's where you go measure it. And then you plot up the number density versus H1 mass. Okay, so the observations are shown here in this band, this gray band here. And then here's some bunch of simulations. So again, the TNG simulation, not bad. SIMBA simulation, pretty good. EAGLE, not so good, right? Okay, so the way they're doing feedback or something might be getting the stars right, but they're not getting the H1 right at all, right? I won't go into too much detail. This is sort of more detail. You can also look at CO luminosity, which is a tracer of the dense molecular gas, so on and so forth. So, okay, so I wanted to sort of get to the meat, well, not really meat, but the fun part, right? Which is what's so surprising about SIMBA? Okay, so I love this movie. It was made by the Camels folks, by Paco Villescusa-Navarro. And what this is a temperature slice in 4 different models. So this one's going to be illustrious, not labeled here. This is SIMBA, and then 2 other flavors of various models, okay, Astrid, Magnetica. Now, one of the key things about SIMBA's, one of the key things about SIMBA's black hole feedback is we really tried to stick to what's observed. And one of the things that's observed about these black hole jets is that they're very bipolar, right? So look at our nice bipolar jets coming out of our galaxies, right? All these sorts of things like that. Their feedback, much more spherical. It's much harder to get this model to work than it is to get, to prevent star formation if you inject energy spherically. So they have to inject a lot less energy to get the same result in terms of the stars, right? And you get down all the way down to today at redshift 0, and this is what it looks like. So this is literally what the temperature of our universe looks like in these 4 different models. Amazingly, all of them produce the same kind of stars, right? Yet, there's huge differences here, right? You might think it might be easy to tell which one of these is right, right? Just go out and look in the real universe. Surely one of them is wrong. Turns out not so much, okay? So to illustrate that, right, one of the things you can do is, of course, look in the intergalactic medium and try to look for neutral hydrogen absorption. Okay, this is something you can see. You have background quasars, shines the light through it. You get absorption due to the neutral hydrogen along this line of sight. And you might think, so this is a SIMBA simulation here, sort of same thing, temperature slice here, and at redshift sort of 10 billion years ago, 7 billion years ago, and today. And here's a model where we just, remember we can do numerical experiments and just shut off things and turn things on as will. So we shut off all our jet AGN feedback. And sure enough, nothing heats up, or just kind of like those other models, right? So the difference between this and this, you might think would be apparent in the neutral hydrogen absorption. Because if you, for instance, if you look through a skewer along this thing, right, you'll get a lot less neutral hydrogen absorption because all this super hot gas here, this is like 10 million degrees Kelvin, right? 10 million Kelvin. So that means that won't have any neutral hydrogen, where this stuff will, right? Okay, so this is the idea of the Lyman alpha forest, right? And so here's some example spectra. Again, in the simulations, you can just repeat this experiment. You can just stick something behind it, measure the gas density along the site, create an H1 optical depth, use your little atomic physics, right? And voila, you get a spectrum, right? So this is the H1 spectrum through just one particular line of sight I chose kind of randomly. And in these three models, but the two ones, let's just look at the green one versus the blue one. So forget the red one, but similar to the green one. The green one has the AGN feedback, so it's the hot one, and then the blue one doesn't. And sure enough, you see examples like here where you see a whole bunch of absorption when you don't have the AGN, but you see just nothing here, right? So the statistics are going to be different. And you can see the temperatures in the case with AGN here along the line of sight are a lot hotter than they were without the AGN, right? So it's really doing this sort of widespread heating. Okay, so that might be something we can observe, and it turns out it is. So here's, don't go into too much detail here. What this is just the simplest possible statistic you can think of. What we're going to do is take all the lines of sight that we can observe, and we're going to compute the mean flux decrement, right? Kind of just stack everything blindly. And that's what this quantity is, this mean flux decrement as a function of redshift. And this has been measured out to, out to fairly high redshifts, just being shown to redshift 2 here. So again, here's the green line is the one with the jets, and then the blue line is the one without the jets, right? And here's some observations, right? All these black points here are all observations. These are just two different assumptions about the overall photoionizing background in the universe, something we have to impose. We don't have a general direct control of that since we're not doing radiative transfer. So this is the more recent determination, and if you look at that, what you notice is that the one with the jets actually agrees a lot better than the one without the jets, right? So crazy enough, the universe might actually look more like this than like this. You can do something a little bit more sophisticated. You don't have to use such a blunt statistic. You can, divide the lines up and count individual lines of various column densities. You get kind of the same answer. So here, they did that with the CAMEL simulation, comparing SIMBA and TNG, which were the two inaugural CAMEL's codes. And the TNG is the red ones, and the SIMBA is the black ones, and the data points are blue. And you can see that particularly in this low density region here, which is where we get the big effects, and these very weak H1 absorptors, that's much better matched. So, okay, so what's it doing to the galaxies, right? So we sort of have talked about a little bit about the intergalactic medium, what's it doing to the galaxies. So again, the nice thing about the SIMBA suite is we have this whole suite of models, and we didn't just turn off jets, we turned off, start with turning off everything, and then we turn one thing on at a time. So if we turn off everything, all feedback, no star formation feedback, no winds, no black holes, no nothing, right? We get this yellow line for the cosmic star formation rate density, right? Way over predicting. This is known as the classical overcooling problem. That's your lingo for today. So we need feedback. If we add star formation feedback, like we have in all these other ones, we can sort of get the we can suppress early star formation. However, it requires putting in the AGN feedback to get this. So this is without AGN feedback, and this is with AGN feedback, right? So you can clearly tell that particularly the jets are the thing, if you sort of look through here in detail, it's the AGN jets, it's those bipolar things. You can also see it in more detail, again, as a function of halo mass. So halo mass is, the mass of the total halo around a particular galaxy versus the stellar to halo mass ratio. So in this case, Milky Way is right around 10 to the 12 here, so right at the peak of this curve. This curve is what's kind of roughly observed, at least a rough fit to the observations. If you, again, don't turn on the jets, it's particularly the massive galaxies that fail, right? You don't get this sort of peak, you sort of get a flattening at this massive end, right? And as soon as you turn on the jets here, you get the nice turnover, right? And the galaxies start to be quenched. Remember, I told you that massive galaxies are quenched. So this color coding shows you how quickly they're generating stars, new stars. And yellow greenish corresponds to essentially doubling their stars over another Hubble time. Okay, so it's sort of a doubling rate. So as long as it's doing that, you're sort of forming stars. But if you're down, you have to be down here and be red, then you're really underneath. You really have stopped forming stars from what you've typically done in the past, right? And you see that without the jets, you don't get those quenched galaxies in the massive end, whereas with them you do. Okay, so that kind of illustrates how but what's really fun is then you can run simulations to understand this physics, right? And this is sort of like hot off the presses stuff, which is really cool because it's the first time this has kind of been looked at in cosmological simulations. Why? Because we're the first one to have these jets, bipolar jets in the cosmological simulations. So we couldn't do it really at Simba resolution. We felt like maybe resolution was an issue, so we went and ran some zooms. Okay, so we ran these hyena zooms. So what's being shown here is a little movie where this is essentially what you would see in the X-rays. This is the temperature map, this is the pressure, and this is the density. And this is a single halo, a single sort of group size halo, where we've selected to have a bunch of AGN events, okay, these jet events. And you can kind of see them here. The movie's pretty jerky, unfortunately, on this. But at the start, essentially, the jets are blowing out in this direction. You can see they're sort of blowing little cavities, right? They're over-pressurizing, and then the jet kind of switches to go in this direction a little bit. You can actually see this sort of thing in real data. So this is the Perseus cluster, right? The Perseus cluster is a nearby galaxy cluster. It happens to have a central elliptical that has very active AGN. It's also forming stars a little bit. And you see, when you process the image a bit, you see all these bubbles, right? And what's cool is that when you then look in the radio to look for the synchrotron emission from the jets, you see the radio jets are lining up exactly where the bubbles are. So the idea is these jets, it's like essentially blowing a balloon through a straw, right? You have these jets that are going out, and then out there as it sort of, finally slows down enough to interact with the medium, it's inflating these cavities. That inflation then does PDV work against the rest of the medium and heats it. And you can ask the question, what is the heating due to the PDV work versus the X-ray luminosity, okay? And in order for the galaxy to be quenched, right, what we have to do is to stop the cooling of the baryon, stop it from losing pressure support and coming down into the galaxy, and then then the galaxy will get a whole bunch of gas that's cold and it'll start to form stars. So we can't have that. So we need something to counteract that heating, right? This is the one-to-one line for counteracting heating. So that PDV work equals the cooling luminosity, which is what you see in the X-rays from Bremsstrahlung primarily. So that would be one-to-one. If you're above this line, you're doing more PDV work than you need to offset the cooling. And what's amazing is in Simba, so the black points are actually observations, right? And then the blue and red points are actually from Simba, right? So not only do we match the observations, but importantly, we have this thing where basically at these low halo masses, below about 10 to the 13 or so, so remember halo mass of the Milky Way is about 10 to the 12, so we're just entering into this regime where we should be starting to do this, right? But we're not quenched yet. We're still forming stars, right? We're actually over-pressurizing the medium and actually evacuating the gas out of the halo. And so then you can go and look in the simulation and ask, how much gas has been evacuated out of these halos due to this process? And the answer is a lot, okay? So again, we have these SIMBA variants, so it's always instructive to look at these kind of variant models. So again, when we turn off all the feedback, what is being plotted here is the fraction of the gas component relative to the dark matter. Now, if you imagine, the dark matter is forming into these structures, like I showed the large-scale structure, you form a galaxy halo. The baryons, they're subdominant mass-wise, so they're attracted in along with the dark matter. And if nothing else happens, you would expect sort of an equal mix, the same mix of baryons, of gas and dark matter that you have cosmically, you would expect that same mix inside the halo as well. That would correspond to a number 1 here for this, right? So this is like you have lost or gained no baryons relative to what you would expect just from the cosmic mean. And sure enough, if we don't have any feedback, that's pretty much what we get, right? And the problem is, of course, this has now been divided into a variety of components, right? So we can say the blue is the stars, the green is the interstellar medium gas down into the cold gas in the galaxy, and then these various other colors, particularly this pink one down at the bottom, this is the hot circumgalactic medium, right? So this is the stuff that for the massive galaxies, we want to keep that hot, we want to not let it cool, right? When you don't have any feedback, or even when you just have only star formation but no black hole feedback, you don't get rid of any of those baryons. You have a lot of hot gas, you have a lot of cold gas, and you form too many stars, right? When you turn on the jets, everything changes, right? The AGN jets really take down this massive end by a huge amount to the point where, these halos in sort of the Milky Way, just above Milky Way type regime, only contain about maybe 30% of their cosmic baryons. The rest of it has been blown out to large distances. You can actually compute how far out you have to go to enclose all these baryons that got blown out, and it's about 20 times the size of the halo in SIMBA. So it's way far out. This actually has huge impacts for cosmology and weak lensing. So the point is, these AGN are really having a huge impact on the sort of the overall structure of the CGM. I won't get into too much detail, but there's a variety of things. But just to be fair to other models, you can calculate this quantity called the entropy, which is just the temperature divided by the density of the 2/3, and compare the radial profile of taking a few of these groups, compare the radial profile of the entropy in these groups to observations. This was done in a paper by my former student, Ben Oppenheimer, in a nice annual review article. That's the data, all these dotted lines. Here's SIMBA, right? So SIMBA is high. So that's not so good. So SIMBA does really well with the Lyman alpha forest IGM. Seems to actually have too much entropy, which means too much thermal heating inside of halos, right? So again, mixed bag, right? Some things are good, some things are bad. TNG in this case seems to do much better, et cetera, et cetera. So, this hasn't been solved yet, but it's I think one of the more interesting problems. Okay, I think my time is up. So yeah, I just hopefully gave you a flavor for how we can use these simulations to explore the coevolution of galaxies and black holes in the intergalactic medium, and they're connected on very large scales. This is a concept known as the baryon cycle, right? For another piece of lingo for you, you'll hear that word a lot, right? That's the idea that there's matter and energy being exchanged over within a large-scale cosmic ecosystem. Galaxies are not these sort of isolated individual things that just kind of evolve on their own without caring about the rest of the world, which is the impression you might get from a JWST image, right? SIMBA shows these differences, particularly owing to this bipolar jet feedback. I would say that despite the fact that it seems to be different than just about most other models in this aspect, so far it's been a mixed bag, right? Some things work better and some things don't. So it's not obvious which one is right. So this is kind of why we do these sort of things. But overall, I think SIMBA, and even other models to lesser extent, suggest that there is this very large-scale connection between the galaxies and the IGM. So, if you're a cosmologist and you only care about the IGM, or you only care about, omega, whatever, lambda, or something like that, and you just want to measure the IGM, the conventional wisdom is, we can ignore those galaxies. They're so far away. Who cares? They're not doing anything to me, right? I don't know about that. right? Especially if we want to do stuff at precision 1% level. I think that's patently untrue, right? And frankly, to be fair, the cosmologists have realized this, right? So, and finally, I just want to point out that all the SIMBA data is publicly available. So if anybody is actually interested, including galaxy catalogs, all kinds of stuff, we have all kinds of public tools to do everything, essentially make all the plots I made here. You can make from our galaxy catalogs or from our absorption line generation software and stuff. It's all Python. So any students interested in downloading and playing with that, just go to that. Enjoy. All right, thanks very much.
Thanks a lot, Romeo. We have time for questions. Se quiserem fazer pergunta em português, também não tem problema. A gente traduz. So let me start kicking it off. Oh, Gustavo has that. I was going to kick it off, but there you go.
Okay, thank you, Romeo, for this great presentation. So let me see if I understood from things I used to hear in the past and now what you're saying. So AGN jet feedback seems to be solving a long-standing problem, I guess, of the type of structure at the galaxy level, right? So this is really what you would say is the solution to this problem. So adding the effect of the AGNs.
Correct.
I just wanted to confirm that this is.
Yes. I think at this point, every single model that I showed you in that picture uses some form of AGN feedback in order to get the massive galaxies right. Many different ways of doing it, but not one of them does not use AGN feedback at this point. No one knows how to do it without AGN feedback.
I see. Yeah. Very good. And then the other thing is more of a comment is like, what happened to Nala?
To what?
Nala, Simba's sister.
Oh, yeah, well, we have to go hierarchically because one is descendant from the other. So Kiara is the next one, Simba's daughter.
So my kickoff question was that many people here may have heard on the general media or something that, JWST observed a galaxy that breaks cosmology and so on. Maybe you can comment on this.
Yeah. No. Okay. Yeah. Right. No, look, observing these high redshift galaxies is very, very difficult. And, look, we're at University of Edinburgh, we had a paper which was kind of similar to that, although it had the sense not to claim that Lambda CD1 was broken and just say that this was it was a redshift 16 galaxy. So it was about 200 million years after the Big Bang, a very large galaxy. It would have broken Lambda CDM, but they were at least, they didn't go around advertising that to the press. Nonetheless, everyone looked at that galaxy and gone, for all the world, it looks real, right? The problem is that, JWST, at least most of those initial data were all in broadbands. So you had like 5 or 6 broadband filters, and then from those broadband filters, you try to fit some model to that of the stars that are in the galaxy, assuming a whole bunch of things, and then say that, okay, well, that's how many stars that are there, and that's how far it is, and so on and so forth. And that's a very tricky procedure. And so, for instance, for this redshift 16 galaxy, it just turned out to be a completely perverse set of very strange circumstances that all conspired to make this look like a redshift 16 galaxy when it was a redshift 5 galaxy, okay? And it just happened to be that there were some very surprisingly strong emission lines just exactly in the region, 2 of them, that landed exactly in the 2 regions where the JWST bands slightly overlap, so they appeared in both bands. I mean, you couldn't have drawn this up any worse, right? And so, of course, the way they figured that out was they went to the director and said, okay, we think this is a redshift 16 galaxy. We can't see anything wrong with it. Can we get a spectra of it? Well, a spectrum takes a lot longer, right? So the director had to allocate director discretionary time to go get a spectrum of it. And when they saw the spectrum, they realized exactly what had happened, right? But nobody had anticipated that this kind of thing would happen, right? The other galaxies, the other group that claimed Lambda CDM was broken, again, you know, they did something that everyone had done and just said that, look, we have all these like really, really big galaxies early on. How does Lambda CDM do that if it's hierarchical? Again, it turned out to be a very interesting answer, that in fact, a lot of these turned out to be AGN, surprisingly. Nobody expected to be that many AGN. But again, we didn't learn that until we got full spectra, right? So it's only when you get something very interesting, then you go and you apply for more time, and you know, with NIRSpec or some spectroscopic instrument, then you can actually learn the nature of these things. So it's very hard work, right, to do this. And you know, people are not necessarily just, you know, trying to be provocative or you know, doing stupid things, but there's always surprises, right? Every time we have one of these things, we learn something new. And in the end, that's fine, right? That's what it's for.
So for this particular question about AGN feedback, I guess what are observations that you are looking forward to that you think can better discriminate between these various galaxy evolution models and these different simulations?
Yeah, I mean, one of the most basic observations that, it's not actually that basic, it's quite hard to do, but you know, but it's at least conceptually very basic, is this plot, right? Measure the baryon fractions in the various components as a function of halo mass, right? Go out and do that. Turns out that basically you can do that, but only above about 10 to the 14, because that's when your X-ray telescopes get, you know, sensitive enough, have enough sensitivity to measure such big things. Maybe down a little bit further than that. And the question is, you know, is this stuff, you know, this is the X-ray emitting gas, this hot CGM. So we can make a very particular prediction for how much X-ray emitting gas there should be as a function of halo mass. Other models make very different predictions. Eagle predictions are up here, right? As of now, it looks like Eagle is pretty well ruled out. TNG is a lot closer, and we can't really distinguish between TNG and SIMBA at this point. SIMBA's on the low end of the data, TNG is on the high end of the data, okay? But again, this should be very, you know, for instance, if we had Athena, or, you know, whatever, new Athena, right? This is piece of cake work, right? This will just be known. The other thing is you could do it with Sunyaev-Zeldovich, right? I think that's a really up-and-coming, exciting area. So you can, again, look at the diffuse gas in order to get an accurate census of the baryons at large scales. So I think, you know, this kind of problem, we will have much better constraints on this. And okay, New Athena is a while away, but eROSITA data, I think, hasn't been exploited to that end yet. So there's data, you know, coming very soon that should tell us these sorts of things. But also, I would like to know about like these jets, you know, and actually can we see these bubbles and things like that in some of these lower mass systems. Right now, for the most part, these bubbles and stuff are observed in very big systems. Again, just sensitivity issue, right? You need the contrast and stuff like that. Now there's a few cases of group scale objects below 10 to the 14 halo mass where you can see bubble-ish things. But again, you know, if we had a lot more of those cases, we can really try to constrain these kinds of statistics and see whose model is turning out to be closer to right. Yeah.
So following up on this question, so do you think that the jets as a feedback mechanism, it's established, or is it still like you have to be proven? And in that sense, I mean, you can try to measure any one of these three phases of the circumgalactic medium there, right? And each one of them would be observed in a different way. Each one of them could be a clue to this. So which one of those, the hot, the warm, or the cool CGM, do you think it's most viable to be observed?
Yeah, so I think, you know, in the region of interest, it's, well, first of all, you can see that at least SIMBA, once you get into the group regime, just doesn't predict a whole lot of warm or cool CGM, right? So it's going to be tough to detect that. It's already tough to detect the hot stuff in X-rays. You know, just as a word, you know, you can detect the cool and warm CGM in absorption lines if you happen to have a quasar that passes close by a galaxy. So we had a whole series of papers that compared SIMBA to those types of CGM absorption line, metal absorption line, to make sure that we hadn't over-evacuated the halos. In fact, we matched that quite well. So, but I think that we're kind of limited to the X-ray or perhaps SZ. That's really, you know, where we have we have leverage right in this group scale regime that we can, this is where all the models differ, right? So how established are the jets? Well, look, we see jets. Like, we see them actually all over the place. So I don't think there's any question that they're putting a lot of energy out there. I just think that the reason why nobody had done this before is basically because, the conventional wisdom was, okay, look, we need to heat the whole halo. So if we just heat these two directions, how's that going to do anything? And, the cluster bubble people told us, oh, there's this PDV, pressure waves, sound waves, hand waves, all kinds of things that happens, and suddenly everything's sphericalized, right? But no one really, people believed it, but it was sort of like, nah, surely this can't be how it actually happens. But at least in Simba, when we put in these jets, that's actually what does happen, right? It actually works, which is kind of cool. And people had shown that it works in very idealized simulations, right? But then people say, well, that doesn't account for inhomogeneities, blah, 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 cosmic growth, et cetera. So, I think it's a plausible model to do that. But again, does it have to be as strong as it is, so on and so forth? I don't know, right? But I think we have to do bipolar jets because, frankly, that's what the real universe does. So the real universe has figured this out somehow. Surely we can too.
Any more questions? Mais perguntas?
I think I can take one. So I actually come from a very different scale, that is a molecular scale. And it was fascinating to see how the multi-scale approach can also be seen on this cosmological view. In your case, you have some issues that is regarding to this, both the space and also the time scales. It's always a question, first of all, how to couple the different scales in terms of either integrated or hierarchical. And also the initial conditions in our case is very simple because you know the atomic structure and somehow you can go on in your simulation. Here, how do you see as the most challenging part in the sense of, is it the time scale, is the coupling between the different scales that you are dealing with?
Yeah.
Or is your model itself that it needs to be looking more detail or something is missing and so on and so forth? Can you comment on that?
Yeah, so that's a good question. Okay, so I think there's two different approaches. One is the one you were just talking about, which is you directly try to implement, connect in a small time simulation. There are people who are doing that. There's famously a group in Finland who have taken a large-scale simulation and then placed the little black hole dynamical model right at the center around the black hole, and fully relativistic and everything, right? And try to figure out black hole growth and mergers from there, right? Fantastic, but of course it's very expensive, right? Because that, as you say, that becomes then the limiting factor. The approach we've used is actually a little bit different, right? It's effectively developing an effective theory, right? It's like what is the thermodynamic laws effectively of supernova feedback? Can we describe it in some macroscopic way, where macroscopic means of order kiloparsec, right? And in some cases, like in the case of the fire simulator, it seems to work really well. Other cases, like black holes, people have been trying this. It's a big mess, right? So it doesn't line up any kind of neat thing, at least that we found so far. So, if you can develop those effective theories, I think that's the most promising approach because it doesn't then bog you down in the whole time step issue. But whether you can do that or not, that's a whole separate question, right? Doesn't always work.
Okay, anybody else? That's okay. Well, if not, then let's thank Ramil again.